Is the microphone on? Okay, cool. Thank you, Roberto, for the prize and for the invitation, and for the introduction. And thanks to the organizers for organizing this wonderful conference. I will talk today about information propagation and entanglement generation with long-range interactions. Because of screening of Coulomb interactions, typical condensed matter systems are often well described by short-range interactions, which for the purposes of this talk I will define as finite range or exponentially decaying interactions. On the other hand, many AMO and other synthetic quantum systems are often described by long-range interactions, which for the purposes of this talk I will define anything except for this, where a prime example is interactions decaying as a power law with distance. Examples include dipolar interactions between electric dipoles such as Rydberg atoms, excitons, and polar molecules, or magnetic dipoles such as magnetic atoms or NV centers. Also van der Waals interactions between Rydberg atoms, as well as tunable 1/(r⁴) interactions and other forms of interactions, say mediated by phonons in ion crystals, or mediated by photons for cases of atoms in multimode cavities or long waveguides. These long-range interactions are among the strongest and most tunable interactions available in AMO, and as a result, they are ideal for studying strongly interacting quantum many-body physics, as evidenced by a large number of invited talks at this conference on Rydberg atoms, magnetic atoms, excitons, polar molecules, ion crystals, and atoms along waveguides. Long-range interactions give rise to a lot of important features. For example, compared to short-range interactions, they allow for faster quantum state transfer, faster quantum computing, and faster preparation of entangled states. They can mask the dimensionality of the system, such as, for example, in the case of all-to-all interactions, where the dimensionality of the system doesn't matter at all. And they can also give rise to unusual ground state entanglement properties. There are a lot of active research areas studying various phenomena associated with long-range interactions, such as, for example, short-time dynamics after a quench and whether there's a speed limit to information propagation, long-time dynamics and how long-range interactions affect thermalization and localization, what happens to topological phases in the presence of long-range interactions, and whether there are new phases and phase transitions that arise because of long-range interactions. So today we'll focus on this first part, which is information propagation with systems with long-range interactions. So to do this, I need to introduce Liebe Robinson bounds. Consider a lattice in arbitrary dimensions, but for simplicity, I will draw one-dimensional lattices. And suppose there is a unitary operator B acting on one of the sites. And let A be an observable at distance r away. Let psi be an arbitrary initial state, and A of t be Heisenberg evolution of the operator A under some Hamiltonian H. Then in order to quantify the effect on the observable A due to disturbance B, what we do is we take the expectation value of A in the state psi with the unitary B applied minus the expectation value of A without the unitary B. Now what we do is we insert an identity in the form of B dagger B in front of this A right here. Then we notice that AB minus BA is a commutator, so we just rewrite it like this. Then we bound this expectation value by the largest eigenvalue of the corresponding operators, which is what these double bars mean. And finally, B is a unitary operator, so it doesn't change the spectrum of the operator, and therefore we arrive at this unequal time commutator, which is the signal at distance r away after time t, and this is what Liebe Robinson bounds place constraints on. In particular, at time equals 0, A and B are supported on different sites, and this commutator is 0. But as time goes on, the support of the operator A grows, and the signal also grows. Let's consider first the case of short-range interactions. Suppose we have a one-dimensional chain with nearest neighbor interactions where each term has the largest eigenvalue bounded by 1. At the same time, let's allow for arbitrary time dependence in these Hamiltonians subject to this constraint. Furthermore, we will allow for arbitrary time-dependent on-site terms of arbitrary magnitude. So in this case, you can bound the signal a distance r away after time t using the following time series, which takes quite some work to derive. The intuition, however, is very simple. The coefficient in front of t to the n is just the number of paths to get from the initial point to the final point in exactly n steps. So it's like a path integral, but all contributions are positive. So Liebe and Robinson wrote this series in '72 and also summed it up to get the following bound on the signal after time t a distance r away, e to the vt minus r, where v is of order 1. If we now set this signal to some constant and solve for t in terms of r, we find that t is roughly equal to r, and that for t smaller than r, the signal must necessarily be small, and for t larger than r, we have the causal region where the signal could be large. This linear light cone has indeed been observed in cold atoms, and what we essentially have in this bound is that the time t to send quantum information over a distance r under these short-range interactions is greater than or equal to r, and it cannot be shorter. This bound has lots of applications. It bounds the rate of quantum communication through spin chains, entanglement growth after quenches, or under other, possibly time-dependent unitary dynamics. It bounds the speed of quantum computers, thermalization rates, and even entanglement and correlations in gapped ground states. So what we would like to do is we would like to extend this Liebe Robinson bound to interactions that decay as a power law with distance. In particular, we would like to understand the shape of this causal region. To be more precise, we would like to find a function f of r such that the time t to send quantum information over a distance r is greater than or equal to f of r. And indeed, these are some of the first experiments and some of the first theoretical works on the subject, but this research area has been really growing rapidly since, say, 2013. So to be specific, now we suppose we have a chain with interactions between arbitrary pairs of sites, where the largest eigenvalue of such an interaction is bounded by 1 over the distance to the power alpha. Again, we allow for arbitrary time dependence in these Hamiltonians subject to this bound, and we allow for arbitrarily large time-dependent on-site interactions. Now we will consider all alpha greater than or equal to 0, and of course for very small alpha, such slowly decaying interactions don't have a well-defined thermodynamic limit, and one usually includes the so-called CAC normalization. Now, if we want, we can include it at the end, but we don't want to carry it around, so we will omit it for now. In 2006, Hastings and Coma showed that to bound the signal at distance r away after time t, you can still write the same time series as for short-range interactions, except the coefficient now in front of the nth order term is still given by the number of paths from the initial point to the final point in exactly n steps, except you can make not only nearest neighbor steps, but you can also make steps of arbitrary length, except the step is suppressed by 1 over step length to the power alpha, which sort of makes sense. Now, to tighten the bound that was derived by Hastings and Coma, we introduced some additional tricks. In particular, we consider breaking down the full interaction into a short-range piece and a long-range piece, separated by some critical range chi that we choose in the beginning. Then we work in the interaction picture with respect to the short-range Hamiltonian, again write the series from the previous slide, and finally optimize over this range chi. There is another trick that we use in a paper that we're about to submit that is based on this quantum simulation paper by Ha and collaborators, where we consider unitary evolution over this region ABC, and we approximate it with forward time evolution over regions B and C, followed by backward time evolution over region B, followed again by forward time evolution over regions A and B. It turns out if this region B is sufficiently large, this is an excellent approximation. And now, if we're interested in Heisenberg evolution of an operator O under this unitary, we see that this operator commutes with these bottom two pieces. So in fact, we can approximate the evolution just by this top piece. And this means that under this approximation, the evolved version of the operator O has no support on the region C, which is what we use in the proof. So now using these and other tricks, we can arrive at the lower bound on the time t to send quantum information over distance r and the presence of these long-range interactions in d dimensions. So let's first consider alpha equal to infinity, which is short-range interactions. And there we get the famous Liebe Robinson bound, of course. Now, for alpha larger than 2d, we were able to get an algebraic bound, which approaches the linear bound here as alpha goes to infinity. For alpha between d and 2d, the best known bound is the one derived by Hastings and Coma, which is the logarithmic bound. And now looking at alpha equal to 0, there the distance between sites actually doesn't matter, because these are all-to-all interactions. However, what matters is just the total number of sites. And in fact, the larger n is, in fact, the faster you could transfer information from one site to another site. As shown, for example, in this lower bound by Lashkari, Stanford, and collaborators. Now, we've extended this bound to other values of alpha that are smaller than d, and also to alpha equal to d, where we show that as n increases, you cannot get a state transfer time that goes to 0. Now, I should point out that these bounds are written for a special case where the number of sites is just r to the dimension of the system, but we have a more general set of formulas for arbitrary relationship. Now, these bounds have lots of applications. They can be used to bound information propagation after local quenches, as I introduced in the beginning. They can be used to bound the growth of connected correlations after a global quench. And they can also be used to show that correlations in gapped ground states fall off no slower than 1 over r to the power alpha. They can also be used to derive entanglement area laws for dynamics and in gapped ground states. And finally, they can be used to make more gate-efficient protocols for simulating long-range interacting quantum systems on a quantum computer. So far, I only introduced the bounds, which is the lower bound on the time t to send quantum information over a distance r for these 1 over r to the alpha interactions in d dimensions on a total of n sites. However, what are the fastest known protocols? It turns out that for alpha greater than d plus 1, there is no known protocol to do better than the usual linear protocol, which is just nearest neighbor swaps from one site to the next. Now, we've recently shown a sublinear protocol for alpha between d and d plus 1. And this protocol also gives a constant state transfer time for alpha between d over 2 and d, as well as a logarithmic time for alpha equal to d. For all-to-all interactions, we have a protocol that goes to 0 as 1 over the square root of the number of sites, and we have its extension for other small values of alpha. Now, this entire graph is not very important. The only important thing is that the only place where the bounds agree with the protocols in terms of scaling is actually alpha equal to infinity, short-range interactions, which means we still have to do a lot of work in order to either improve the protocols or more likely tighten the bounds. Now, we're actually pretty close at alpha equal to d, because you see that we have a logarithmic protocol which agrees with a bound for all alpha just above d. And we also have a bound at alpha equal to d that agrees with a protocol just below d. So we're really close, but we're not quite there to get saturation at alpha equal to d. So in the remaining 10 minutes, I will present our protocol for this logarithmic state transfer at alpha equal to d. So I will show that we can do state transfer over distance L in time that's logarithmic in L using 1 over r to the d interactions in d dimensions. So why is this interesting for this audience? One prime example of this is precisely our favorite dipolar 1 over r cubed interactions, between arrays of dipoles in 3 dimensions, such as, for example, Rydberg atoms and V-centers, polar molecules, whatever you have. And then this really fast state transfer protocol can speed up quantum computing algorithms, and it can also allow for fast preparation of a wide range of entangled states, including states that are useful for metrology. Now, in order to demonstrate this state transfer protocol, let me first show how to prepare a GHZ state 0, 0, 0 plus 1, 1, 1, 1, 1 of linear size L in time that's logarithmic in L. So to explain the protocol, let's first start with a simple case of 1 over R interactions in 1D. So I assume that interaction over distance R falls off as 1 over R, and the nearest neighbor interaction has strength 1. Such a case can indeed be realized in trapped ion chains. And now the key is that we will be using individual addressing of our qubits to turn individual interactions on and off. So here's the basic idea. We will first start with the first qubit in the state 0 plus 1 and all the other qubits in state 0, and then we will double the size of this GHZ state in every step. And the number of doubling steps, of course, to get to the size L is logarithmic in L. So the only thing that remains to show is that each doubling step takes constant time. So let's show this. Suppose we've created a GHZ state of size R, and we would like to double it to size 2R. And let's call this first half A and the second half B. So what we need to do is we need to apply a controlled NOT operation from any qubit in A as a control to every qubit in B as a target. And in that case, indeed, every qubit in B will join this GHZ state. So the way we're going to do this is we will be applying 2 qubit Hamiltonians between a qubit I in region A and qubit J in region B, which implements a controlled X rotation of qubit J controlled by qubit I. So this is the Hamiltonian. It falls off as 1 over R by our assumption. And then if qubit I is in state 0, then it does nothing. I here is the identity. And if qubit I is in state 1, it rotates qubit J around the x-axis. And then, of course, if we wait for the right amount of time, it will precisely implement this controlled rotation of qubit J from state 0 to state 1, so that qubit J will join this GHZ state. Now, what we're going to do is slightly different. We're going to apply all of these guys at the same time. We're going to apply this controlled rotation where for every I in A and for every J in B at the same time. And since all of these guys commute, it's actually very easy to understand what happens. So in particular, to be clear, we're applying all of these guys, these, and these at the same time. So if we look at this qubit that's the furthest away and that's experiencing the weakest coupling, we see that what happens is that every one of these guys are trying to do a controlled rotation of this last qubit. And the rotation rate of this last qubit is bounded from below by the number of controls, which is just R, times the weakest coupling, which is just 1 over 2R, which is this full distance. And then you see that the 2 R's cancel here, and we get a rotation rate that's actually independent of R. So it takes time independent of R to double the size of this GHZ state, and therefore it takes logarithmic time to grow our GHZ state of size L. Now, something very similar happens for 3D and 1 over R cubed. So what we do is we double the size of the GHZ state in every step, and it takes logarithmic time again to build the whole state if each doubling step takes constant time. So it remains to show that a doubling step takes constant time. So suppose we've built a GHZ state on these green qubits, and we would like to have all of these other guys join the GHZ state. Now, this red qubit in the corner has the weakest interactions, and therefore it joins the GHZ state last. And its controlled rotation, that is controlled by all of these guys right here, is bounded from below by the number of controls times the weakest coupling. So the number of controls is just R cubed, And the weakest coupling is given just by 1 divided by this main diagonal to the power of 3. And this main diagonal is basically r up to factors of order unity. So again, r cubed cancels, and we get a time to double the GHZ state that's independent of r. And so we can build a full GHZ state of linear size L in time that's logarithmic in L. So we can create this GHZ state again in time that's logarithmic in the linear size of the system. Now, we want to extend this GHZ state preparation protocol to do state transfer over distance L in time that's logarithmic in L. And it's actually very simple. So again, what we would like to do is we would like to start with an unknown state A0 plus B1 in this red qubit and send it over to this blue qubit right here. So to do this, we assume, again, that the red qubit is in the unknown state, but all other qubits are in state 0. And then what we do is we just implement our protocol from the previous slides to prepare the GHZ state, which allows us to encode this state in the full system in this GHZ-like fashion. And then we undo this GHZ preparation protocol, except we spatially invert it such that the state gets mapped instead of the red qubit, it gets mapped on the blue qubit. And since each step here takes time that's logarithmic in L, that's what we showed in the previous slides, the full state transfer protocol also takes logarithmic time. So as an outlook, we would like to tighten both the bounds and the protocols to achieve saturation, such that protocols agree with the bounds. We would like to, and then these improved bounds and protocols will help us improve our understanding of equilibrium and non-equilibrium properties of long-range interacting many-body systems. And they will also allow us to speed up, but also to bound the speed of quantum computing, quantum simulation, classical simulation, and the preparation of entangled states, including the ones that are relevant for metrology. So with this, let me thank my group members as well as the funding agencies. The people who led this work were Mike Fosfeig, Ming Tran, Zach Eldridge, Joshua Ngong, and Andrew Guo. And it was also done in collaboration with Jeremy Young, Jim Garrison, Andrew Childs, Yuan Su, Ali Hamed Mousavian, Charles Clark, Fernando Brandao, and Spiros Mikalakis. And with this, let me thank you for your attention.